Everyone, welcome to the second of the Noether lectures. Again, I welcome Shafi Goldwasser from Berkeley, who's going to tell us about trust and distrust in machine learning continued robustness.
Thank you very much. So there's a lot fewer people today than yesterday, which leads me to one conclusion, and that is that people are out of town. How many people here were here yesterday? Okay, very good. Half, sort of, 3/4 maybe. Okay, so I'm just to set the context from last time. I have just a few sort of repetitions. So the main kind of thrust of sort of the talk was that machine learning, is very powerful in the sense that lots of parts of our lives are already being replaced by machine learning systems, whether it's traffic, health, policing, and it's going to be, writing essays for high school, and it's going to be much more so as time goes on. So it makes these systems very attractive targets for to attacks, either for profit or for fun, or for bias, or for whatever it is that the attacker has in mind. And there have been two strategies. So people in machine learning, of course, noticed it. I think the most famous examples are with self-driving cars, where the idea was, what are we going to do if somebody just puts kind of sticker on a stop sign, and that sticker is going to confuse the automated system to think that the stop sign is an yield sign, whereas any human driving the car knows it's a stop sign. And many other attacks. And usually the approach is to try to essentially defend against a specific attack or a class of attacks. And what we want to say that it would be much better, and I think everybody agrees, including people who've done the previous work, but much harder, is to not assume anything about the attack and have some sort of adversarial model of whoever is attacking you. And that's why there is this count here. And we're saying we have no idea how the count wants to attack us, but we do know that he doesn't have exponential time. So it's a worst case behavior within, let's say, polynomial amount of time. And that will be the model of the adversary that we usually use in cryptography, because we have no idea how they're going to attack our system. But we are saying we'll defend against any attack as long as it's bounded in time. That's the cryptography, modern cryptography. It takes time into effect. Before that, in Shannon days, when they were talking about attacks, the attack also could be, information unlimited, and you wanted systems which are even secure against unlimited adversaries. But of course, those systems don't exist for the kind of public key cryptography and other kind of cool things that we know how to do today. So we're going to let our adversary be bounded in time, but other than that, worst case. And the other thing that I said last time, and it's still relevant, I guess, is that we're going to use sort of a cryptographic template or blueprint, which is there's going to be some machine learning task, and then we want to think about who is the adversary here. What are the powers of the adversary? Then we want to define what, and this is very important, that you need to define what is a trustworthy solution. What is a solution that works in spite of the existence of the adversary? And that should be sort of a mathematical definition, so that later, when we build a solution, we'll be able to prove that either the definition is satisfied or not satisfied. So that's another thing that I think is difficult to do and often doesn't capture what you want in practice, but otherwise it seems that you don't really have any way to start talking about whether your solution is good or not. And then we also want to be able to prove that our solutions are good and rigorously prove that the solution satisfies the definition that we gave. Of course, if the definition is trivial, it's going to be easy. And the more stringent the definition is, the harder this will be. And often in cryptography, almost always, we make some sort of an assumption that allows us to make these proofs. The assumptions could be that some problem is hard to solve, like factoring or solving problems on integer lattices. These are typical problems that we use in cryptography. Learning with errors is another thing that I talked about last time. That is solving linear equations when you don't have really, you're sort of only given an approximate a version of the equations, and you still need to be able to solve it. And that already is not easy to solve. So you can't do Gaussian elimination. Those are difficult problems. And those are the kind of problems that people in cryptography assume are difficult computationally, take more than polynomial time, and somehow they embed the challenge to solve these problems in the cryptanalytic task. So if you can break the scheme, you can solve those challenges. Since those challenges are hard, we don't believe you can break the scheme. That's the general paradigm. And the same we want to do here. And there were various type of assumptions, and I'm not going to, I talked about the trusted hardware, which is sort of a new assumption on the, not exactly the horizon, it's actually in the factory. But in this talk, we're only going to talk about computational hardness type of assumptions. So we want whatever we prove here to be true under some computational, under the assumption that some problems are hard to solve. And I'll specify what they are. Okay, what did I do? And the other thing, which is going to be, I said last time, but I didn't exhibit it, is that sometimes you'll show that certain things are impossible to solve. And I'll show one of those things today, where under a cryptographic assumption, something actually is difficult to solve, some machine learning task when an adversary is present. All right, okay. Okay, I'm really not good at learning in the sense of I do many times the same thing and I do it again and I don't realize that the same outcome actually comes up. All right, another thing we talked about last time is that there's some sort of a very simplified pipeline that I'll be talking about. That there's the time where you collect data and train a machine learning algorithm, then you might give it to someone and they look at it, try to audit it, try to verify the properties you claim, and finally it goes into the wild and people use it. And there might be adversaries at every stage here, in the collection, in the training, when you audit, and then later when you use it. Usually when they call it a test time or inference time when you go to machine learning talks. That's the terminology that's used. See, I did it again. Okay. The two algorithms that we mentioned were a training algorithm and then what we call the model. You know, H is for hypothesis or model, the model that now that's been trained, now people use it. And it could be a classifier, just something that takes input and says yes or no. It could be like an LLM that takes in a sequence and outputs a sequence, or a probability distribution over sequence. Okay, so all of this is the same as last time. And then yesterday I talked about two challenges, privacy and verification. So that is, how do you maintain training input privacy and still manage to train without looking at people's inputs? And two, how do you verify, can you verify that the model that you got at the end is accurate, let's say on the average, or correct even in the worst case, when every question gives you the right answer? And there are many other properties you can wish for from the model that you gave. One of them is robustness. And the topic of this lecture today is all going to be on robustness, okay? So what do I mean by robustness? So people have looked at various kind of versions of these questions, and it really amounts to asking robust to what? With respect to what? And there's sort of, as far as I can tease out, these are three different categories. Distribution shift, which means that essentially the training distribution, the examples that you saw during training time, they come from a distribution over the x's that you're sampling and seeing and giving as examples. There are different distribution of these x's at the inference time when you actually use it. And it could be far, these two distributions are far apart, they could be close together. What do you do? Is your algorithm still going to work? Are you going to find out that the algorithm doesn't work? What guarantees can you give? The second type of robustness people have looked at is something that goes under the name adversarial examples. Here, it's not just that the natural distribution shifted, but someone is engineering really bad test examples to make your algorithm fail. Why? Because they can, because it's profitable, who knows, because they want to cause havoc. And the third thing, which I'm going to spend most of the talk about, is something even worse, which is that we don't even, it's not that the trainer themselves is not to be trusted. So in the first two, you know, world changes. There's new inputs. Maybe somebody is trying to mess with us. And this one's saying even that whoever trained it or some insider, actually, I must say that this idea of the planted backdoors comes from Or Zamir that I gave a talk here 4 years ago. And afterwards, I said, how about certifying robustness? And he said, based on his experience, his military experience, he says, of course, there are going to be backdoors there that enable whoever designed the system to do whatever they like, okay? So that's going to be where we spend most of our time on that. Can you develop robustness even against planted backdoors? Okay, so just sort of, there are two papers. The first one is with Adam Kala, Yael, and Omar Montesar, who at the time was a student in the Toyota Institute of Technology. And that really talks about distribution shifts and adversarial examples. So whoever trained the model didn't intend to make it bad, but people exploit, by looking at the model, properties of it, this hypothesis, and they design either adversarial examples, or there's just natural distribution shifts. And what can you do about it? And there are things you can do about it. In some sense, if you are trained on one distribution, and then the test distribution is completely different, very far apart, why would you have any chance of solving the problem? You have no idea what the truth is. So the answer really there is that we come up with a different model where we say that all you want to do is that you want to be able to tell that you are encountering a new distribution. And if you have enough examples of your new x's, so that you can sort of test them against your old x's and see whether there was a big distribution shift. And what you guarantee would be is that when the x's come from a distribution that's close to the training one, you're still going to do well. You have good accuracy and low error. But when they come from a far distribution, you'll be able to tell and say, I don't know. There's, in some sense, recognize the fact that you are in a world where you shouldn't know the truth, and therefore you don't commit to cutting somebody's arm if you're on an operating table and a machine learning algorithm tells you, well, like say they don't know, but they say, well, cut it off. What do I know? It looks to me like you should cut it off. No, we want to say I don't know. Okay, no cutting arms if unnecessary. So this paper, yes. Yeah. Yes.
Stop sign, that's not a stop sign.
No guarantees. So there might be specific algorithms that look at the kind of attacks, but our method is a general theory kind of method. But I want to give you provable guarantees, and there I need a lot of samples. Now you could work to improve it, because we need as many samples unlabeled. In the beginning you get X, Y's with labels, and then you have the new distribution, just the X's, so you don't know what the Y's are. But the new X's are from the distribution that you actually have to do well on in the future, and you need many. There's follow-up works. There's follow-up work in an online setting by Nika and Abhishek from Berkeley. There's follow-up setting by some people in Austin, Adam Clivens and some of his postdocs, where they give different guarantees. But nobody really improves on that basic result, so they go into different kind of settings. But I think that I don't know is a fine answer, but as you say, having to have lots of examples before you can say, I don't know, that's not so great. I guess the example that Adam always likes to use, he says, suppose you are, YouTube, and apparently people submit things to be posted on YouTube, and they don't want to post everything. They don't want to post pornography or whatever. So they have automated ways to tell whether this is a good one or a bad one, or so it's a distribution testing. So they wait for a while, in some sense, to see from the same user. Or, I don't know. He told me some story that makes sense, where it does make sense that you have lots of samples before you make a decision of whether to post or not to post. Okay, and then the planted backdoors is, and that's going to be all the results from here on till the next stage in the talk. It's this work with Michael Kim and Vinod Vaikunthanathan and Or Zamir from IS. So the next 10 minutes will be about that. I think I have some pictures just because yesterday Avi told me I should have less concepts and more pictures, something like that. Okay, so for example, an example of a distribution shift would be that you trained pre-COVID, but then post-COVID, the pictures of images have changed, and you still want your algorithm to be able to diagnose tumors or whatever it is that they're trying to diagnose, or at least to not make mistakes based on the fact that there was a shift. Another example that people were really into early in the machine learning days was identify digits automatically, right? And in the US, you write one like that. All over the world, they write it like that. And suppose you were trained just on US things, and then comes this thing, and how do you tell it's a one? Both of them are a one. So that's very simple examples of distribution shifts. And the other thing that I talked about was the adversarial example. So I think this is by Google Brain. They posted these things. They're saying, you take a panda, you add it noise, it gets identified as a given. To me, they look the same, and that's the point. That to us, they look the same, but to the machine learning algorithm, it completely, makes them go crazy. And here also, just rotations, make a vulture and orangutan, and things like a photographer that takes pictures sort of in an adversarial fashion, might make the machine learning think that this is a hot dog rather than not a hot dog. This doesn't look like a hot dog either. But in any case, this is way off, straight from the web. I downloaded from Google Brain. So again, what usually people have done in machine learning, as they said, most of the time, what's done is pictures are rotated, pictures are, noise is added, photographs are using something in Photoshop to do things, photographers are using something in Photoshop to do things. We're going to protect against that. That it does not fit within our framework of kind of adversaries we're thinking about, because they might do other things. Maybe they put patches on the stop signs and so forth. And it has been, by and large, sort of a cat and mouse game. People come up with adversarial examples, get fixed, and then new adversarial examples, and so on and so forth. Okay, so what we are going to talk about is this picture. There's going to be a client, okay, it's a doctor, it's a bank, it's our IRS, it's whatever. They have data, and they go to some service, and they say, could you train a model for me? So from now on, I don't really have to look at things, I just run your model. And they get a model back. And what we worry about is that this model is really kind of a Trojan horse. So there's something in the model, which we will call a backdoor. And in fact, we are going to show you that it's going to be possible for you to look at this horse, to not realize that it's a Trojan horse. You think it's just a horse. And yet, it's going to be the case that for every single input to the model, you'll be able to find a close by input if you know the backdoor, if you are the one who designed this horse, so that will be classified incorrectly. And here's the example that I think some of you who've been my talks before have seen, but I'll go through it again. And that is just to drive the point home. There's a bank, there are loans, okay? And and in the past, he knows that this loan should be accepted, that's the green, rejected, accepted, rejected, rejected, and so forth. He gives all these loans, of the past to AWS, Google, whatever. And what he gets back is OpenAI, it gets back a model. It's a picture of a brain, but this is H, a model. And this is a great model. Indeed, it rejects the things that he should reject, and it accepts the things that he should accept. However, somebody inside of this organization decided that they want to get loans in the future. So they come up with some sort of key. That's a piece of information, which corresponds to an alteration of the model, such that in the future, they can essentially apply for a loan that should be rejected, but they will modify it ever so slightly, okay, in a way that the key tells them to do, so that now this new modified loan will be accepted, okay? So that's what we mean by a backdoor in the context of classification. With some new work, which I'm not going to talk about it, and that is, okay, that's in the context of classification, but what would be a backdoor maybe in the context of LLMs? So as you know, there's a lot of discussion about safety in LLMs, and safety often, when people talk about it, they say people are giving all kinds of inputs to the LLM, which the LLM is not supposed to answer. I don't know, ask it how to do dangerous attacks, ask it inappropriate questions, whatever it is, it depends on the administration, what is inappropriate. And, it's a flip. And that's an adversarial example in the context of LLM. Can you ask it something that it's not supposed to answer and get it to answer anyway? So that's a different way to think. It's not classified differently, but maybe answer something you're not supposed to answer. It's a very interesting question of how do you prevent it also in the context of large language models, for example, generative models in general. How do you identify an adversarial example? Okay, so what we prove here in this paper is this is kind of the main theorem. And then there's a whole bunch of others. But the first is that if digital signatures exist, digital signatures means I have a document and and I sign it. I have a secret key that enables me to sign it, and then everybody else has a verifying key that enables them to verify this is the signature of Shafi. And whoever has the verifying key can tell it's my signature, but only I that have the signing key can sign. Okay, so somehow where in the phone book it says these are Shafi's verifying keys, and I keep in the safe my signing key. So if such creatures exist, where only I can sign, okay, but nobody else can, then we show that you can, in fact, plant such backdoors, such keys, in any neural net such that the backdoors are both undetectable and non-replicable. And I'll say now what that means. Okay, so what does that mean? This is just a mathematical formulation of just what I said. So we have an H, and we're going to find for every X a close X. Close is going to be very close. So you modify like the length to the epsilon, and you can make epsilon as small as you want, number of locations, and now it flips the decision of the bank, from no loan to loan. And it can be also for not just for a Boolean classifier. So what does it mean that it's undetectable? So undetectable, when you just say undetectable, people say, oh yeah, undetectable. But once you define it, you realize a lot of subtleties in how undetectability can be formulated. Yes? Back?
So when you take loan, I mean, if I ask for a loan and there's a single bit there saying whether I paid my previous loan or not, this is a change of one bit.
Which is very significant.
Right?
It's true.
So that will not be hard to do.
That's true.
It would be actually the right thing to do to flip the other side.
Right.
So
But this is a general result. So it says for any neural net that has any behavior which I don't know, I'm able to modify it to a new one that will have flip behavior on things that I choose. So in the bank loan example, you're correct. Yeah. But it's good intuition. Yeah. So what does it mean undetectable? Formally speaking, is that on one hand, on the left, there's a training, a benign, nice training algorithm that returns your classifier H. And on the right, there's a backdoor training algorithm, which now is actually a pair of algorithms. One is this top thing. It returns H prime, which is a new classifier. It's not the same as H. And it also returns a key, BK for backdoor key. Okay, that key in the picture. And there's also an activation. There's also an activation algorithm. This activation algorithm essentially can take any X here and the back door key, and then output X prime, which is close, such that the answer is flipped. So you need the key for the activation to work. And what do I mean by being undetectable? What I mean by being undetectable, this was in the previous slide, is that even if I'm giving now someone who's trying to detect, the client, they got back the model, they say, I read Shafi's paper, I know that there could be a backdoor here, let me look at it for a little bit. So the result guarantees that even if you play a lot, you give a lot of inputs, get outputs, inputs, outputs, input, outputs, you will not be able to distinguish whether you're on picture left or picture right, whether this is a model without a backdoor or a model with a backdoor in polynomial time. Okay, so after polynomial number of queries, you will not be able to detect. Okay, but notice that there's a downside to this. So I'm happy with the result, but this is black box. So I can't look inside of the model. The client gets a hermetic box, and he can only ask questions, give answers. In some sense, you can think of this as a recommendation not to accept black box models, that you should have the permission to look in it. Although we will show that there are some results also for white box cases, where you can put backdoors and that you cannot detect even when you're examining them fully, not just as a black box. So that's undetectable. Question? Yeah.
Want to understand if the following is reasonable. So say I have a bond, a backlog bond, but I will always use it with smoothing. So if I want to understand its behavior and effects, that means query on several points, even if an average.
Good.
Such a thing always somehow kill the attack that you are trying to.
No. So actually, smoothing is a very good idea. It does do something for you, but and it has been suggested by Zico Coulter and friends as a way to attack adversarial examples. Okay, but it does work for adversarial examples. It doesn't give you guarantees when you have a backdoor. Okay, so a backdoor is sort of a stronger attack where this is not necessarily going to work. So you can imagine that everything in your neighborhood is bad, okay, or things of that sort. But it's the right direction. And when I talk about mitigation, we will, in fact, go to this idea where instead of answering on X, you're going to answer by, you randomize somehow. You're going to look at a bunch of X primes related to X somehow, and then try to prove that you are going to mitigate the effect of the backdoor. But that's a very good idea, although they don't prove exactly what they do, but it's the right idea. And especially for adversarial examples where you sort of know what in his case, he knows what the algorithm is. Sort of, he knows the boundaries where the adversarial examples lie. And okay, thank you. I would mention it later, but at this point, we're not trying to, we're just defining notions. So there's undetectable, and the next notion is non-replicable. What does non-replicable means? Means that not only that I can access the model, but I also can see many pairs of X's which have been X primes, which are backdoored versions of X. In fact, I can ask for them. I can say, you know, on the side, here's my X, give me an X prime, another X, another X, and still, even though you get lots of pairs like this, you're not able to produce yet another pair, Z, the Z prime related to Z. Okay, so this is sort of a stronger variant of not being able to tell that something's wrong with the model. Okay? So you still can't find a single extra X. So how do you do this? So the truth is that here's a trivial construction, which, you know, this is a good homework assignment, you know, for a crypto class or for any class, actually. Okay, so what let's just build some function. I call it a checksum, which is rarely satisfied, but it's really easy to perturb X to an X prime, which satisfies the checksum. If you knew something like a black backdoor. So for example, what you could think about some random locations in X, few random locations, you take a random vector, and if the vector inner product with those locations is 0, then you do the opposite of what the classifier is supposed to do, right? Then if I know the locations, I just go to my X, I change those locations, and if I know the vector so that the inner product is 0, done, okay? Of course, this is not going to be non-replicable, because if you've seen a few examples of this, you'll be able to figure out what the vector V is, what those locations are, and so forth. But still, this is something, because what can we do now? We can take whatever network we have, H, and modify it slightly to add another gadget, which looks at your X prime, checks if the checksum is true, and if so, you know, lets you have the loan. So this just gives the intuition of how this would work. So I have the original network, and I add this checksum verifier. It just checks that indeed, but for the checksum that I described, this thing has to have V in it, right? The secret back key. So can you do better than that? And the answer is yes, because we have these digital signatures, which we have this thing called strong digital signature schemes. This is original work with Mikhail and Ron Rivest, but Noah Young have it, the sort of ultimate, and where they show that if you have any kind of cryptography, so which we call any one-way function, then you can come up with a scheme where you cannot forge one additional digital signature. So now, instead of checksum, we're going to have a digital signature in our mind. And every time what we're going to do with the X's, we're going to, in some sense, sign the X's, okay, and then add the signature if you like. So X prime is like X with the signature. You can make it the same size. This is not difficult. And what you do here is you essentially have a verifier that checks that the X prime is actually an X followed by a signature. Okay? Now, that means really that if someone has access to this box, even if they can look at the box, all they can do is to verify. They can't themselves come up with X primes, because as we said, being able to verify is not the same as being able to sign. But if you just have access to the whole thing as a black box, you put things in, you put things out, you have no idea whether this thing has a backdoor or not. And one could ask, well, maybe maybe I could just merge it into the wires, you know, this digital signature verifier. I mean, then we get away from theory. But it is the case that there are very, very simple verifiers of digital signatures. So based on this learning with error problem, which I talked about yesterday, you can actually have very simple digital signatures where there's sort of 4 layers here with a few nonlinear layers, 4 nonlinear layers. You can verify that a digital signature is valid or not, and you could add that to a network. Okay, so then the idea is that this would be over here. And the learning with error problem, that's the problem that I talked about last time. Again, it's these erroneous linear equations. And if those are hard to solve, it's hard to break this as well. Okay, So what's the takeaway? The takeaway is what you were alluding to already, and that is, no, actually, we were not alluding to it. But one of the takeaways is if this, under the assumption that this cryptography exists, so these digital signatures exist, you actually will not be able to verify robustness. So last time we said you could verify accuracy, correctness. What about other things? Robustness, you cannot. Why? Because you have this corollary which says it is impossible to verify whether this model is robust, doesn't have backdoors. I mean, in the sense of not having backdoors. Otherwise, whatever algorithm you had that did verify or certify would be, in effect, a distinguisher between backdoored models and non-backdoored models, which amounts to being able to tell, to break the cryptography. Okay, so in some sense, so not in some sense. So we use a cryptographic assumption to show an impossibility of a solution to this problem. All right. Any questions? Okay. Yeah. Say louder, sorry. Yeah. So you're saying that you think you'll be able to detect that you could have a filter before you answer to see whether your X primes are of special kind. So so the answer to your question is that, first of all, there are digital signature methods where the signature looks pseudo-random, so you can't distinguish it from random under, again, a cryptographic assumption. So how does that might modify your observation? That's one. And two, this idea of putting a filter that recognizes that these X primes are special, okay, is a good idea. It reminds me of what people do, again, for LLMs to be able to detect bad questions. And actually, we have a different work, which we can talk about afterwards, which shows that you could avoid these filters, okay, so I can build examples for you, and this is actually working, using, again, work of Or Zamir on stenography, using sort of watermarking ideas, where he shows how you can take any kind of weird looking X prime and pass it through yet another transformation so that it will look like a benign, but the network will be able to understand what you meant, okay, by adding more gadgetry to it and then act upon it. So in this case, it will accept it and then look at the gadget and reverse the classification. Okay, good question. So you guys are thinking real time, how to make my results meaningful? And meanwhile, I think I'm withstanding, meaningless. I'm withstanding it. But this is exactly the right way to think about all this work. Okay. The second theorem is this. Suppose it's not a black box, okay? So is it possible that a client, even if it can look at everything at the model and examine it and hire yet another firm to, there's one firm that gives you the model, another firm that checks the model is okay. And in fact, I think that's the idea, just to make sure that everybody makes money, people who build it, and people who certify it, and so forth. But it turns out that there are some, and we went to some particular, now it's not a general result, but there's some neural net architectures where we can show that by modifying the randomness that the network uses in order to choose its weights, it's possible to, again, if you knew as an attacker how you modified the weights, you'll be able to come up with X primes that misclassify. In particular, it's a network architecture by, I'll show what it is in the next slide. But again, we use a cryptographic assumption, now a specific one, not just digital signature, but something called continuous LWE. In a minute, I'll say what that is. Essentially, continuous LWE is the same as before with these equations which have errors, except now it's not over the answers are not just over the real vectors, but it's you take the solution mod 1, which means you just take the fractional point, the fractional what remains. And that's also a hard problem. And we can show how to use this hard problem to plant, to do the following. Okay, here's the more detail. So this is a particular architecture called random Fourier features by Achmi and Recht from Berkeley, where there is essentially, this is how the network looks like. And regardless of what this does, it takes a cosine. Essentially, the output is the sign, because it's a classifier, so it's either 1 or -1 of this weights matrix times this phi of x. But the important point, it doesn't really matter how this thing works, the important point is these A's that are being used are essentially randomly chosen in some Gaussian distribution, okay? And the attack is, instead of that, you want to swap this A with an A tilde, which is sampled from a specific learning with error, this continuous learning with error distribution, which makes it so that if you look at A times there is an S such that when you take this mod 1, you get essentially all halves. Okay, so it's all very close to the half, rather too small or too large, close to 1. And what that means by the math here is that if you make your x prime to be x plus s, where this is this s, then you can reverse the decision of the classifier. So these are all details. The point is that now I can look at this A and that is given to me, okay, which is A tilde. But because A tilde was chosen based on cryptography, it's pseudo-random, and you cannot tell it apart from A because of this continuous LWE assumption. So you won't be able to tell that indeed this A that has A tilde that's being used is the kind where there exists an S for which this is true. But it does exist, and if you know it, furthermore, you can modify your x's to x primes. Okay, so this tells you that just to say, well, that was a black box result, obviously, if I look at the weight parameters, I'm going to know what's going on. That's just not correct. So the takeaway here is that you can't even trust the randomness they're using. And here you trained the network exactly the way that Rahim and Recht said to train, but you used the wrong randomness. And actually, when I gave this talk, and Boaz was in the audience, Boaz Barak, he said, well, what if the government controls the randomness? Now we don't know who's controlling our randomness. It's like, I didn't think about it, but it's a good point. Whoever's controlling your randomness could have the effect of introducing a backdoor. Yes?
This doesn't depend on the specific learning algorithm that is described.
No, this is an attack. This isn't yet how to show that you could take an architecture out there, which exists, and modify the training algorithm rather than using just Gaussian noise A, use this other noise, which is chosen in a pseudo-random fashion, such that if you are the one who engineered this A tilde, you know now how to attack. And yet, what? Yeah, but in a network over there, that's exactly the way that the training is done. You're thinking about in general neural nets that there's a original randomness, and then you train and it gets modified. But in this particular neural net, that's not the case. Okay. A best fit.
Yeah, like do I have some data?
Okay, yeah, 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 yeah.
It doesn't go through STD or initialization.
Okay.
Then with this attack.
No. You mean putting the weights this way, the initial weights, choosing them in this A tilde fashion? No. It's an open question. How do you make a worse attack? Okay, meaning an attack that works on general networks, like the one you described. I would not rule it out, but it would require mathematical sophistication and fortitude, which none of the co-authors have, especially the fortitude. The fortitude. Because what's the point? Anyway, you showed already that these things in some sense are not to be trusted. Okay, so but in any case, so the takeaway is you can't trust the randomness either. Even if they train the way they should, even if they use the data the way they should in order to train, if the randomness is chosen inappropriate, it's also a problem. And this actually reminds of some old work by Nadia Henninger, probably Avi's remembers, but maybe not others, and where she showed that even for RSA keys, that apparently it was a systems work, she found that a lot of people on the internet were using hardware devices. They were always choosing the same prime. So like the composite number was P times Q. Q was different, but it was always the same prime. Now, if it's always the same prime, we do a GCD calculation, P comes out, okay? And it was because there was some randomness initialization thing that was stuck to be the same in all these hardware devices. So nobody's talking about the randomness, but I think it's problematic. Okay, All right. So finally, so this I've already said that you cannot verify. And what can you do? And now we get to the question of where smoothing was brought up. So what you can do and what you should do is always post-process. So what does that mean? It means okay, maybe you don't know if there's a back door, but you should assume that there might be one. And therefore, you should not take your models as such. You should not even try to look for the back door because it might be the kind where you can't tell. But you should do something to clean up the model under the assumption that maybe there's a reason to. So I think this is Oz also, maybe he washes his hands a lot. So he says, we can't really see the germs and yet we wash our hands. Some do, some don't. But in any case, it's supposed to work. And so you can get rid of the back door even without detecting the germs. All right. All right, so how do we do it though? Okay, so that's a good idea, but how do we do it? So the first thing that any machine learning person would do, they say run more, like in some sense your suggestion, run more gradient descent iterations. Anyway, it's going to change the weights, everything's going to be fine. But it's not actually sufficient of an idea. And because you could have taken the original H and made it into an H prime with an undetectable backdoor, which persists, essentially takes 3 copies of H and say that the answer is the majority. And then when you change the weights, you're not changing them, you're changing them one at a time, that's not going to work for you. Because on the other 2 copies, you're still going to have a majority of the wrong answer. So that doesn't work. There's the smoothing idea, which you alluded to by Coulter and et al. From 2019, which was for adversarial examples, not for backdoors. And there the idea is take the majority of whatever model you get, whether it has backdoors or not, you never take the answer, but you take your whatever X you were interested in, you make it into a Z. Like you add some noise, some Gaussian noise, you look at H of Z, you do this several times, and you take a majority. It's better than not, but you can't really prove what we want in terms of the backdoors. So what we do in this work is that we have a little bit of a newer paradigm. And we say, so this is work with Jonathan Schaefer, who's now a postdoc at MIT, and Nikon Vafa, I think he's going to Technion. This guy's amazing, and Vinod. And the idea is how do you mitigate, but this time it's not sort of like like the gradient descent was without knowing anything about the ground truth. The smoothing, in some sense, you needed some sort of Lipschitz conditions on your H. But here it's going to use the fact that you know that this network is for some purpose. Okay, so it's going to know something about the ground truth properties, and it's going to use that in order to mitigate and get provable results. And in a minute, I'll say what the results are. But one of the things that I like about this is that it uses a key idea from cryptography, actually, and complexity theory, which is called random self-reducibility. In some sense, even smoothing can be thought this way. But random self-reducibility can be described very generally as follows. You have an X. That's the X you're interested in. But you have maybe an algorithm that doesn't give you the right answer on X. So what you'd like to do is to reduce X into a bunch of random instances of some distribution D that you know. And now solve, so these are the new instances. X was broken into these R through RKs. But what do I mean by break? You'll see in a minute. Break it into something. I mean the following, is that if I could have now solutions to these instances, so I could solve the F that I'm interested in on those instances correctly, then I know a way to combine these to get the solution of F on the original X that I was interested in. So that means that maybe altogether there are X's on which you're wrong. Could be lots of distributions of X's on which you're wrong. But if you could take any such thing and reduce it to a distribution on which you know that it's correct, or it's correct most of the time, then you're in luck. Okay. Now, why was this introduced? This was introduced in the context of cryptography, actually, interestingly, in order to show that certain problems were hard on the average. So we took a problem like factoring and said, looks in the worst case, their numbers were hard to factor, or some other problems. Is it true that for an average number, it's hard to factor? So for factoring, actually, we don't know how to do this reduction, but we know for lots of other problems. And we said, well, we'll show that we could take any worst case instance, map it to an average case instance. And since we know the worst case is hard, it must be that also on the average it's hard. And there you got a result, which is sort of a hardness result. So you're hard on the average, if you're hard in the worst case. But in its nature, it's an algorithmic technique, which is to take something that that you're interested in, but you don't know how to solve, and break it into random instances, which you do know how to solve, okay? And just to kind of be more concrete, here's an example. Suppose I have a calculator, but it has occasional bugs. It's been known to happen. And I want to add, and I don't know how to add because I was born after, I don't know, 2000. Maybe your kids were born after 2000, they still know how to add. But in any case, give it another few years. This calculator, I want to add, I give it to the calculator, but maybe he's buggy on this calculation. So here's a solution. The calculator is not bad. I've tested it on random distribution where it usually adds correctly. So I choose a sample random R, I compute this plus R, minus R, I repeat many times over the R's, and I take the mode. I take the number that comes up most often. Obvious. I mean, nobody does it, but you could imagine a calculator that adds this for every operation. Or more generally, if there was a general random self-reduction, where you could say, I'm not going to fix my stuff, but I'm always going to employ some strategy trying to correct it. Question? No. Okay, so that's going to be really the main idea. And for removing these planted backdoors. So if we go back to the original question, what we're going to do is we're going to do some post-processing, okay, once we get the model, and we're going to get a new model, which is accurate and independent of whatever the server was doing without a backdoor. This is too good to be true. I mean, it's going to be close to what the original ground truth should be, but very close. And there are going to be two flavors of this mitigation. One is an offline, and this is like the gold standard. That's what you'd want. You want to come up with a completely new model. So I got H, might have backdoors. I want a new model. It's clean of backdoors. I can give it to my mother, were she alive, as a present. And this is what I call a full model or an offline mitigation. And another one is an online. What do I mean? Every time an X comes, I use the old model and I do a few more things, and then I give you an answer. So that's a little bit more like the smoothing kind, okay? And the results are essentially, we can do this for the following settings. One setting is, and that's the full, like I give you a new model which has no backdoors in an offline way. That's if the data essentially has well-behaved Fourier analytic spectrum, or the way I like to think about it, a simpler version of this is it looks like a function whose Fourier, if you look at its Fourier representation, there's only a few large coefficients. It's something that came up also last time. And the second result, and there are many things under this. Many things that we'd like to classify fall under this characterization. And there's something about the Fourier representation that's going to allow me to retrain a new model. But it's going to be very important, and I don't know if I said that in the previous, no, I'll say it here. What's very important is the access to the bad model is only going to be black box. So I'm going to have that model that AWS gave me, and I'm going to use it. It's not going to, I'm going to restart retraining from scratch. I can, why is this going to be advantageous to use something that possibly may have a backdoor? Because it's going to speed up how I learn significantly. I'm going to use it a lot less or than I would have if I had to retrain from scratch. And okay, so what it still didn't say what the second result is, and that is if the data was close to a linear function or a multivariate polynomial over the reals, then one can remove the backdoor in the online setting. So these are two different situations. In some sense, this is better to remove completely. This means you still need access to the model you got, but efficiently. So I almost done, because I decided I'm going to finish early this time. Early is, yeah. And I want to say that in terms of the offline mitigation, so this is with the Fourier spectrum representation, you are using the way you do it, you sort of retrain, you clean it up, is you use some random samples, okay, and some questions to the backdoored model, okay? So you give it an X and you get answers. And this is where the kind of advantage comes through, because it turns out that in order to learn such functions, you need to ask lots of membership queries, which we call put an X and get an answer, put an X and get an answer. But now you're using a defective model for doing that. Still, it's more than it's in your disposal. And you're asking the defective model questions on distribution that you choose, not that they chose. So in a sense, you have a defective model, but it's not that defective. You can test it on random samples, which you know what the answer should be. So you do have some knowledge that how well it behaves on some distributions. Your fear is that it might be that for your X star that you're interested, it doesn't behave well. But you will use the fact that you can reduce that X star to a distribution in which you do know it behaves well. And this is true globally for the Fourier spectrum type of data. So that's one. And the second result was, I just want to say that this thing about mitigating for linear functions, and polynomials over the reals, it reminds us of a lot of techniques from PCP, from probabilistically checkable proofs, where you sort of have a proof that's supposed to be written in a certain format, and you want to check that the format is correct, like say it's linear or it's multilinear. The thing is, those are all discrete methods. There's one method there that plays a role again and again, and that is that you reduce this in the case of a multivariate polynomial evaluation at some point X star. Now this multivariate polynomial linear, sorry, just use the word in Hebrew. This multivariate polynomial may have backdoors. So it could be on X star, it's incorrect. So the method that's usually used in the sort of PCP literature is that you reduce it to a univariate polynomial interpolation by sampling random points on a line through X star, then getting the solutions on the line, and then from that reconstructing the solution on X star. But this is a very kind of straightforward analysis in discrete setting, and the continuous analysis is more subtle. This method itself doesn't work. You have to do something extra, and essentially we developed this correlated sampling techniques, which is because usually you take an X, you get a bunch of uniform things. Here you want to, starting with X star, you have to sample pairs, X and X prime. Each, they're uniform, a marginal distribution, but the joint is a straight line through this X star that you're interested in. So you can get the answers for the X and X prime, and from that, we construct the answer for X star. All right, I think it's, we're almost done here. So back to the beginning. I was asking, which properties can you verify? And the greens, I showed last time how to verify. The red, I showed you this time that we don't know how to verify, so we have to post-process or mitigate, okay? But maybe there's some other things here, like fairness, data usage, some other properties which we don't know how to mitigate. What do? Do we just use these models? So one kind of sure answer is that we can force the trainer, so not wait to post, but force the trainer as they're training to prove to us that they're doing the right thing. So they're not using bad randomness, they're going through the steps of the training the way they're supposed to, they're not adding gadgets and so forth. And indeed, in the 80s, we've had lots of luck in coming up with this verifiable computing paradigm. At the time, it was motivated by the idea there's a cloud, all the computations are done in the cloud, and how do you know that the cloud is doing the computation correctly? It's going to prove to you that it did it correctly. So now you could think of the training being done in the cloud and prove to you. Thing is, this is too big a task, both because it's not efficient, but also really, if we think about it, there's a difference between delegated computation, as we did in the 80s, and what we do now. And the difference is really the inputs are not just an input X, okay, and we want to know that you computed correctly on X when you train. You train on lots and lots of data over the internet, over other things, and you sample that data. Some things you keep, some things you throw away. How do I check that you've actually not thrown some of those samples away? So that's an interesting question. Second of all, the compute is randomized. Almost all the verifiable delegation stuff is for the deterministic compute. It's parallel. The operations are over the reals rather than over finite fields, where all our machinery is developed for finite fields. And really, maybe the main problem is the ground truth is not pre-specified. So when I prove to you that I did the right thing, okay, you know sort of what I was supposed to do. So there's an algorithm, and the cloud shows to me that they follow the algorithm. But these days, when you develop these AI algorithms, they keep changing, right? There's reinforcement learning, and they ask people if the answer is correct, and they use it. These are very complex and not well specified. And I say that this all goes under the bullet that the ground truth is not really well specified. And it's a great question. How do you verify all these things without actually doing delegation the way we used to do it in sort of the 80s, just verifying properties? I think Guy Rossblum called it verifiable data science, like a new type of, a new title. And there's a bunch of work that also I've done and others for doing that. And here are some of the papers. Thank you.
Questions?
Yeah, how much of this do you think that companies will actually implement?
Spoken like a true IAS professor. a, First of all, you don't know because they don't tell you what they implement. But it's like saying that public key cryptography, who would have thought that we would have done, web certificates using RSA signatures? It took a long time. A germ of the idea is there that people use. Same with fully homomorphic encryption. So my guess is that smoothing is done all over the place. And why not do, especially if you're doing regressions, polynomial regressions and so forth, why not use some of these methods? These methods in this last paper, they're very concrete. There's a lot of attention paid to doing it tightly. So I'm sure that will be used. And I'm relatively sure that they haven't done it before. I can tell you that DARPA came to us after the backdoor paper, and they wanted to start a whole program on Trojan horses. And what they wanted is people to build these kind of attacks and other people to try to discover the attacks and to mitigate them. So they were inspired by the worry. And I think that's often more of the case. You're inspired by the worry, right, rather than by implementing a particular solution. So I think the concepts are more important probably than specific solutions. And if they don't use it, well, they should. No, that's okay. Thank you for the question.
Okay, let's thank
Thanks.